Right. So in previous sessions, we learned about the force acting on a current carrying conductors. Right. Current carrying conductors are kept in a magnetic field. Uh, right. So F is equal BIL, the expression. We got F is equal BIL, where B is the uh, magnetic flux density and I is the current through the conductor and delta L is the uh, length of the conductor. Right. Sin theta represent the direction, right? Direction between the current, direction of current and the magnetic field, right? So when they are perpendicular, the maximum force would be induced, and to find the direction of force, we used the Fleming's left hand rule. Then the same BIL sin theta equation we modified, right? Using that, we derived the force acting on a uh, charge as well, right? Force acting on a moving charge, actually, not a stationary charge. Force acting on a moving charge in a magnetic field. So F is equal BQV sin theta. Hmm. F is equal BQV sin theta. Here V is the magnetic flux density. Q is the charge of the charge, right? Amount of charge. V is the velocity. Right? Sin theta is the direction between velocity and the direction of uh, the magnetic field, right? Right. Then we talked about the Hall effect. Right here is this Hall called Hall effect uh, when electrons propagates through a conductor, right? Conductor like this, they would induce a magnetic force downward. Right? Using the Fleming left hand rule, you can find there would happen there would occur magnetic force downward, right? And due to that, what would happen? Electrons would be accumulated on this bottom part of the conductor. Electron would be accumulated on the bottom part of the conductor, and due to that electrons on the bottom part, it would get negative charge, and the top part would be positive charge. Right. So in electric field, we know this is something similar to parallel plate. The electric field in a parallel plate, two parallel plates. Right. So uniform electric field would be induced from the positive terminal to negative terminal downward. Right. So electrons would be, now there would be a electrostatic force, right? Electrostatic force acting upward. Previously, there was a magnetic force acting downward. Now, due to this new electric field, there would be electrostatic force acting upward. Right. So there comes an instance where this FV and FB become equal. Right? Then what would happen? When FV and FB become equal, they get cancelled out. And magnitude becomes equal, then they get cancelled out, and these electrons would not be shifted either to upward direction or downward direction. The electrons would move in a straight line. At that voltage, right? That voltage corresponding to this instance where this Fe become equal FB is called the Hall voltage. Hall voltage. So what you have to remember is when a Hall voltage is reached, the magnetic force acting on the charge become equal to electrostatic force. Then from that we found that this Hall voltage is equal VD. D is the length, right? D is the length in the direction of, right? D is the length of the conductor in the direction of electric field. Right? Thickness of the conductor in the direction of electric field. Right? So this you can easily actually derive this equation. What you have to remember is this: V is equal Fe. When Hall voltage is reached or under steady state, Then here consider a rectangular shape conductor, and using the drift velocity, the equation of drift velocity I is equal to VdA and this are current electricity part, and this newly found whole equation for expression for whole voltage, we were able to derive this another equation for whole voltage using the current, right? Using the current BI over TNE. T is the thickness in the direction of magnetic field, right? In the direction of magnetic field, T, right? So D was the thickness in direction of electric field. N is the number of free electrons for unit volume, and E is the charge for electron, right? So magnetic, today we are going to actually find this B. How to find this B? We are going to find an expression for B today, right? Right. So before that, let's consider how people first found that a current carrying conductor, right? Current carrying conductor generates a magnetic field around it, right? So a small experiment, right? So this is a current carrying conductor. This is a current carrying conductor. Right, so this is a current carrying conductor. And this is a small sheet, right? Sheet, right? Maybe a paper sheet. Right? So this current carrying conductor this current carrying conductor is inserted through this plane sheet. This plane sheet, and let's say current is I. Current is I. Then right, some sort of a small grain, let's say iron. Iron particles are just laid on, arbitrarily laid on this plane sheet. Right, arbitrarily laid on this plane sheet, and when this current flowing through the conductor, let's say I, right, this plane sheet is somewhat vibrated. Right? So when this plane sheet is somewhat vibrated, so it was found that this dust, right? This is not dust. This is iron, small elements of iron metal, right? These iron elements would form around this plane sheet in a circular manner. In a circular manner. In a circular manner, because we know the iron is a ferromagnet, right? So they have magnetic properties. They would be attracted towards a magnetic field. So here it can be concluded that around a current carrying conductor, a straight current carrying conductor, there is a circular shaped magnetic field going around it. Right? Circular shaped magnetic field going around it. circular shaped magnetic field going around it. So this is a small experiment that people first did to find the or to observe the magnetic field induced in a current carrying conductor. Right? So here, these are small particles or small elements of small particles of iron. Fe. Right, so here when the plane sheet is vibrated, when the plane sheet is vibrated, and when the plane sheet is vibrated under current, right? So current should flow through the conductor, right? If current does not flow, then a magnetic field would not be induced around it. So definitely current should flow. And the current carrying condition, right? Under current carrying condition, under current carrying condition in the conductor, and under current carrying condition in the conductor, the iron particles the iron particles would be would form a circular shaped rings around the conductor. Form a circular shaped ring, a circular shaped ring around the conductor. So since iron iron is a ferromagnetic element, ferromagnet, it could be concluded that a magnetic field is induced around a current carrying conductor, around a current carrying conductor in circular manner. In circular manner around the conductor. Right, so this is just a small experiment. Done to find this, down to found uh, that a magnetic field would be induced around a current carrying conductor. Yeah? All right. So next we will find this this expression for this magnetic flux density using Biot-Savart's law. Before that, quickly you can uh, take this down, smart, and after that, let me know when you finish. Okay, sir. Done? Yes. Right. Then let's move on to Biosavart law. That this is the basic principle. Like Gauss law. We learn Gauss law has the basic principle to uh, find the electric field intensity. Right. Likewise, here the Biosavart law is the basic principle to find the magnetic field intensity, magnetic flux density around different shapes of current carrying conductor. Different shapes means always current carrying conductor is not a straight wire, right? It could be a coil shaped one or circular shaped one, different shapes. Right? For any shape, we can use the Biot-Savart law to find the magnetic flux density. That's the Biot-Savart law. Right, so consider arbitrary shape, an arbitrary, consider an arbitrary shaped, consider an arbitrary shaped conductor, consider an arbitrary shaped current carrying conductor through which I amount of current flows. The magnetic flux density or distance, the magnetic flux density or distance away from delta L length, a small segment, right? Delta L length means small segment of the current carrying conductor. Distance away from delta L infinitely small length of the conductor can be expressed using Biot-Savart's law. Biot-Savart's law. So let's consider arbitrary shaped conductor, right, through which I amount of current flows. So it's a conductor. Arbitrary shaped conductor through which I amount of current flow. Then let's say this is the small delta L element that we are focusing on, delta L. And this is the point where the magnetic flux density is needed to be found, right? And the distance from the delta L infinitely small element to the point P right, to the point P where to the point P where the magnetic flux density is needed to be found is R. R. That R. Right. Then this small magnetic flux density. It's a delta. A delta. This is a delta. It's a simple delta. Delta V. Delta V. Since we are considering only small amount, right? Small amount, the small delta L amount. So the here we would get the magnetic field magnetic flux density due to that small delta L amount. Therefore, I will use delta B, right? Small, infinitely small amount of magnetic flux density due to that delta L length. Right, so it is found it is proportional to the current flowing through the conductor. Right, that is obviously. So if the current is higher, the magnetic flux density should be higher, and as well as this length of the infinitely small element, right? Delta L. And as well as this angle. That sine value of this angle between the current direction of current and the line connecting the infinitely small length delta L and the required point P. The sine value of the angle theta between the current direction of current and the line connecting this delta L and P point. Sine theta. And it is found inverse proportional to R square. That is obvious, right? Normally in other field section as well, it was inverse proportional to R square. Then combining all these four, and right, by combining all above relation, right? I delta L sine theta over R square. And we know what is done to usually get rid of this proportion time. Constant should be constant, right? Constant should be applied. I delta L sine theta over R square, right? So this constant is found, right? So constant is found to be using some advanced mathematics. This constant is found. It's found to be that K is equal mu naught over 4 phi. Right? Mu naught over 4 phi. So this here mu naught is called the permittivity of the magnetic field permeability. Yes, permeability of the magnetic field. You notice the permeability of the magnetic field. Permeability of the magnetic field. Permeability of the magnetic field. That's then by substituting for the above expression 1. So this delta B can be written as mu naught over 4 5 I delta L sin theta over r square. Sin theta over r square. So this is the Biot-Savart expression derived from the Biot-Savart law. Right? And this I delta L is called the magnetic element. Magnetic element. I into delta. Magnetic element. Right? Right. So this is the basic expression for Biot-Savart law. Basic expression can be derived from Biot-Savart law. Delta B. So this delta B represent not the total magnetic flux. The small amount of magnetic flux induced due to the delta L part of the delta L small segment of the conductor, right? Right. So actually we have to use the integration here to find the total magnetic flux. We have to use integration. Right. So here we will look at those things. So this is the basic expression for Biot-Savart law. So delta B is the magnetic flux density, small magnetic flux density. Okay. Right. Magnetic flux density due to delta L amount. Magnetic flux density due to delta L length. So I is the current. To the conductor. Delta L is the infinitely small length. Length of the conductor. Theta is the angle Theta is the angle between the direction of current theta is the angle between direction of current and theta is the angle between direction of current and the line connecting delta L length and then the point where the magnetic flux density the magnetic flux density needed to be found. Right? And R is the distance. To the point where the magnetic flux density is the magnetic flux density needed found from delta L element. Right. And this value of so value of mu naught over 4.5 is 10 to the power minus 7 Henry per meter. And so this would be given in the examination. This value would be given this so that note mu naught of 4.5 is equal to 10 into 10 to the power minus 7 Henry per meters. Right, so this is the basic expression for the Biot-Savart law, and we'll see how to apply this basic expression and find how to find the magnetic flux around a straight wire and a coil and a circular shaped current carrying conductor and likewise. So first you can take down this, right? On Biot-Savart law, you have to write this part. This mu naught of 4.5 would be given the value. Right, so I'll give some time. You can note this down. So when you finish this part, let me know, then I'll scroll down.
How is it?
Done this part. Okay. So here you have to understand this basic law. It's delta B, right? Only give the magnetic flux density due to this delta L small element, right? Not the total magnetic flux density. This is not the expression to find total magnetic flux density at a particular point. This gives just the part, yeah, just a small portion of magnetic flux density due to delta L element.
Okay, sir.
Then yeah, so this is to find the magnitude of the magnetic flux density. So to find the direction, you already know how to find direction of the magnetic field using Maxwell right hand. So this Maxwell clockwise corkscrew rule also same thing, right? Same thing, just different names, right? So here, so this means if we consider a screw like this, so there are threads going on. Right, so in order to, right, so this means you have to at this Maxwell clockwise corkscrew. So this represents, so this is a screw, right? This is screw, typical screw. Right, so you have to point this screw. You have to insert this screw in the direction of the current. The direction of the current. Let's say current is flowing into the board, current flowing into the board. Into the board, then you have to point the screw towards the current, or you have to insert the screw towards the current, which means you have to rotate the screw in clockwise manner. Right? Clockwise manner. You have to rotate the screw in clockwise manner to insert the screw into the board. Likewise, if the current flowing outward from the board outward from the board outward. And so you have to rotate the screw in anti-clockwise manner. So here this here the magnetic field is clockwise. Here the magnetic field is anti-clockwise in direction. Clockwise direction. Magnetic field is anti-clockwise direction. Anti-clockwise. Anti-clockwise direction. So this is, I mean, almost identical to the right hand rule. Right? When our thumb is pointed towards the when our thumb is pointed towards the direction of current, the other four fingers gives us the direction of the magnetic field. Right? So if you consider it for the first case, so if you consider it for the first case, so you have to point your thumb into the whiteboard, then the other four fingers will point it in clockwise direction.
The right hand, right? Right.
Yes, right hand. Right hand rule. Not Fleming left hand rule. Right hand rule. Right hand rule. When thumb is pointed towards the direction of the current, the other four fingers are directed towards the direction of magnetic field. And this is similar actually. So since this is in syllabus, I included it here, but both same, right? The right hand rule and corkscrew rule are similar. So here when the corkscrew is rotated in the sense of current, the direction of rotation gives the direction of magnetic field. Gives the direction of magnetic field. So this right hand rule and Koch's rule are similar. So you can use either this rule, Koch's rule, or right hand rule to find the direction of magnetic field. So either any of these two could be used to find the direction of magnetic field. Right? Magnetic field. I think the right hand rule is more convenient, right? That is more easily you can use use that right hand rule.
The difference?
No difference
So
here.
depending on the way the corkscrew is rotated, no, this one changes. So if the corkscrew is rotated towards, the right, towards clockwise, that means current is flowing into the board, like that.
Yes, so if the current is flowing into the board, you have to in this always this screw should be moved in the direction of current, right? According to this rule, this corkscrew should be moved in the direction of current. So in the first case, it is current flowing into the board. So you have to rotate this in clockwise direction to insert the corkscrew into the board. Likewise, in the second one, now the current is flowing outward from the board. So you have to rotate. So you have to move this corkscrew in the direction of the current. In the direction of current. In the direction of current without interchange, you cannot interchange the direction of the corkscrew. Right? You have to keep the corkscrew in the same direction. And you have to rotate. So now current is flowing outward. Right? Current is flowing outward like this. Right? So you have to get this. Right? So we have to get this corkscrew outward, right? Away from the board. So in order to do that, this need to be rotated in anti-clockwise manner. So here you have to, the difference is here you have to imagine corkscrew. If you use the right hand rule, then you don't have to imagine about corkscrew. Just point the thumb in the direction of current, then other four fingers would give the direction of the magnetic field. Right? Okay. Right. Next, the next one is the important one. Some derivations from the Biot-Savart law. Right, so we are going to find three derivations. First one, the magnetic. Right, so here we will mainly focus on three derivations. Here we will mainly focus on three derivations from Biot-Savart law. Biot-Savart's law on conductors, on current carrying conductors, right? On current carrying conductors. First one is if the current carrying conductor is infinitely long straight one. Right, so magnetic field infinitely long straight, infinitely long straight, infinitely long straight current conductor, infinitely long straight current carrying conductor. This dashed line represents it is infinite long. No end. Right? So let's say we want to find the magnetic field here. Distance r. Theta. And the delta L amount. So the magnet, according to Biot-Savart law, the magnetic field, magnetic flux density at point P due to this delta element is mu naught 4 phi I, so current is I, delta L sine theta over r square, right? Only due to the delta L element at point P, right? So here we have to use integration, right? So we have to use integration, right, from minus infinity to plus infinity, right? So the maths students can try that, right? Use integration. Integration would be found the total magnetic flux density at point P is mu naught 4 phi 2I over r square, not r square, r 2I over r. Right? Total magnetic field, magnetic flux density at point P due to this straight infinite long current carrying conductor is mu naught or 4 phi into 2I over r. Into I get cancelled out, 2 get cancelled out, then we have mu naught 2 phi I over r. Right, so this is the expression of the magnetic flux density, right? Magnetic flux density at a distance of r of an infinitely long current carrying conductor, straight current carrying conductor. Right, so using integration, you can try this actually. What you have to do is integrate from minus infinity to positive infinity. Right. Otherwise, you have to remember this one. This won't be given examination expression. You can integrate and go to this expression, or otherwise remember. So that's the first expression. We have infinite long straight current carrying conductor. The second one actually we can easily derive without integration. One is easily derived. We can easily derive the second one. And so here, you know what is I and R. I is the current to the conductor. R is the distance to the distance to the here actually R is perpendicular distance. Right, R is the perpendicular distance. Let's say you are given a current can conduct like this, infinite long. Then you asked to find the magnetic flux density here. In P, so you have to get the distance, the perpendicular distance. R. So I is the current through the conductor. R is the perpendicular distance. Perpendicular distance to the point, the point where magnetic flux density, to the point where magnetic flux density needed to be found from the conductor. That's the second one is the magnetic field at the center of magnetic field at the center of a circular loop, circular contained conductor. Magnetic field at the center, right? Not anywhere else, at the center of a circular magnetic field at the center of a circular shaped current carrying conductor. At the center of a circular shaped current carrying conductor. Magnetic field at the center of a circular shaped current carrying conductor. Magnetic field at the center of a circular shaped current carrying conductor. Right. So this is the current carrying conductor. Circular shaped dot. right? So at the center, let's consider this delta L element, right? So center C, current is I through the conduct, circular shape loop. So you can see here the current and the line connecting the point center and the delta L is perpendicular. Right, so according to Biot-Savart, law, delta B at the center is mu naught 4 phi I delta L sin 90. Sin 90 over, let's say distance is R, the radius is R square. So phi I delta L, so I 90 we know it is 1 R square. Right. So this is due to this delta L element, right? Then if we consider another adjacent delta L element, let's say this is a delta L element. So we get the same expression like this. We get the same expression. Right? So distance is R and 90 degrees angle to the direction of current. Right? So we get the same expression like this. So what, in order to find total magnetic field, what we have to do? We have to just right? We have to just add this delta BCs. Right? So the total magnetic total magnetic flux density at the center, right? Total magnetic flux density at the center is, let's say, BC is the addition of this small part of magnetic flux density. So delta I R squared. So this is a constant, mu naught is 0.45 R squared. I is constant. You can get them out. So this is the sigma notation. Delta L. Right. So the sigma is delta L, small delta, add small delta L elements. Then we get the total length of the conductor. Right. So total length of the conduct is 2 phi R circumference. Right. So which sigma delta L represent the addition of small delta L elements. So what do we get? Yeah, when you add all these delta L elements, circumference. circle is 2 pi r. Circumference is 2 phi r. Circumference is 2 phi r. Let's say if there are n number of turns, right, this circular loop might not be only having one turn, let's say 2 turns, 3 turns, it could be 4 turns left. So if number of turns is let's say capital N, then total length is this total length is 2 phi r into N. Right, so we can so you get the idea, right? There sigma delta L is the total length of the conductor. If there is only one turn, is 2 phi r. If there are n number of turns, it is 2 phi r N. Right, so then the total magnetic field intensity at the center is by I r squared r. So 5 get cancelled out, 1 r get cancelled out, 2 get cancelled out. Mu naught I N over 2 r. Right, so this is the total magnetic flux density at the center of a circular current carrying conductor having n number of turns. Right? So this can be derived using basic mathematics. I think it is good to remember all these things, all these expressions. Or maybe for MCQs, you might not. If we can derive this using a couple of seconds, then okay. Otherwise, please remember this. So I is the current through the conductor. N is the number of loops or turns. R is the radius of the circular. Yes. Third one. Right. Next one is coil. Right. The final one that we are going to discuss. Magnetic flux density along the axis of a long solenoid carrying current. Magnetic flux density on the axis. Axis of a long magnetic flux density on the axis of a long solenoid. Magnetic flux density on the axis of a long solenoid. Axis of long solenoid current carrying conductor. Something like this. Right? So current is I. So this is the axis. That's point on this axis. That's magnetic flux density on the axis of a long solenoid. This is a say on the axis, not anywhere else. On the axis of a long solenoid current carrying conductor. That actually total magnetic field at A is mu naught Ni. We have to use some advanced mathematics to integration to derive this. So it is easy to make this better. You remember this has this mu naught Ni. Mu naught Ni is the magnetic flux density at the on the axis, right? On the axis of the solenoid. Right. Ba mu naught Ni. Mu naught Ni. Mu naught Ni. So here I is the current through the conductor. N is the number of loops per unit length. Or number of turns per unit length of the solenoid. Right? And minus one number of turns per unit length. So for example, if the total number of turns are 10 and the length of the solenoid is, let's say, 2 meters, 10 divided by 2 give the number of turns per unit length. Number of turns per unit length. Right. So these are the three expressions or three expressions that we have to know in according to our curriculum, right? First one is the magnetic field around an infinite long straight current carrying conductor. Second one is the magnetic field at the center of current carrying loop, solving loop. Third one is the magnetic field on the axis. Right, on the axis of a long solder. Right. Right. So you have to take this down. Savart law and as well as this corkscrew. Right. So quickly write this down. So under Savart law, you have to take all these three applications of Savart law. Right. So student who are in mathematics, combined maths can try this. Using integration, you can easily derive this first one. BP is equal to mu naught I O to phi r. Right. So take down this. So quickly write down this and let me know after finish.
So can you scroll down? So up to the end of infinitely long, to the end of the topic, infinitely long straight current can conductor.
Here, eh?
Yes.
So you have to take down about 3 of the applications. So use the space, manage the space.
So can you scroll down to the end of the second topic? So could you scroll down?
Here, the simple n represent the number of turns per unit length, and the capital N represent the number of turns or loops. So the second one actually can be derived easily using basic mathematics. For other two, we had to use integration. So I think it is good to remember these three expressions.
Done, sir.
Then we will let's try some questions. So first try this one. The first one. First one. A current flows down long vertical conducting wire. A neutral point is located at the same distance of 4 cm from the wire. If the horizontal component of the Earth magnetic flux density is 4 × minus 5 Tesla, find the value of current. Take mu naught as 4, 5 × minus 7. Try this one.
So the number of turns, how do we get? Did you count it?
Number of turns, it is not needed because this is the current long vertical conducting wire. Right? Long vertical conducting wire. So this is the wire. This is a wire. So for a wire, what is the expression for the wire? It is mu naught
Mu naught I of 2 pi.
I over 2 pi r. No, number of turns not needed. Right? So we want to focus on this point at 4 cm. They say at 4 cm distance from the current carrying conductor, a neutral point is located. Neutral point means having zero magnetic field. Magnetic field. So which means, right, at this point, the magnetic field due to the current carrying conductor and the earth magnetic field should get cancelled out. This get cancelled out and be 0, right? Right? Somehow neutral point means no magnetic field. The magnetic field into the current carrying conductor and the magnetic field into the earth should get cancelled out there.
The 2 amps, 2 amperes,
Sorry?
2 amperes.
2 amperes. So here at point O, the magnetic field should be equal to the magnetic field of the Earth magnetic, right? Then I is equal, so 2 phi r into 0.10 to the power minus pi mu naught. Mu naught is given. It's given for 5. Is 4 centimeters. So we have to convert it to meters. Mu naught 4 5 10 to the power minus 7. The minus 2 minus 5 isn't it 8 amperes? 8
amperes.
8. Right, so that's how it goes. Then try the second one. A circular coil as shown in the figure, right? So figure is this. Right, so this is 90 degrees. This radius is 4 centimeters. This is 2 centimeters of current flow. Like this, 2 amperes. Right, so I'll find the magnetic flux in the center. Oh, BO. You'll find BO. The basic equation for if it is a total circle, right? If it is a total circular loop, for a total circular loop, what is the expression we have? For the magnetic flux at the center, for the total, it is mu naught Ni over 2R. At here, right? Mu naught Ni over 2R. Ni over 2R. But this is for a total circular loop, but here it is not a total circular loop. Here it is it consists of two circular loops. One is a small one is quarter circular loop. The bigger one is three-quarter the circular loop. You have to consider about that. And 2 ampere current flows. That's all. With this section, right? So this, when you consider this section, right? These two sections, which are pointed towards O, right? Which are pointed towards O. What is the sign theta value? Theta value is 0, right? The direction, the angle between the current carrying conductor and the line drawn connecting the current carrying conductor and the point where the magnetic flux density is needed to be found. At this angle is 0. If you consider these two lines, the angle is 0. So sine 0 is 0. So these two sine 0, 0 means total expression delta B equals 0. So these two segments of this structure, right, would not contribute to any magnetic field at the center. The total magnetic field at the center is due to this small arc and this bigger arc. Right, so try to find that. So here the number of turns is 1. Number of turns in the circular coil is 1. N is 1, capital N. Right, so total magnetic field at the center is due to the magnetic field of arc A, segment A, and magnetic field of segment B. Because right hand screw, using the right hand screw rule, you can find. So when your four fingers are pointed towards the current carrying conductor, the magnetic field is pointed by the thumb. Right here, the total magnetic field actually coming out from the. So this is the direction of the magnetic field. See right hand rule, you can find direction of BA plus BB. So BA mu naught I 2R A, but since it is a quarter of 3/4, A, yes, 3/4 of the total circle, we have to consider that. The total circle is 2/5 radius. Of that, we have to get 2/4, 3/4. So 3 to 4, right? Plus mu naught I 2RB 2, 5, 104. 2 by 104. I is 2 amperes, so 2 get cancelled out. 2 get cancelled out. I is common. I 4 is common. 5 is also common. A plus R B. So mu naught is 4.10 to the power minus 7. I is 2 amperes. Five. Four. RA 4 centimeters. Minus 2 plus 1 over 2 in 10 to the power minus 2. Minus 7. So you get 2.46 or 1 in 10 to the power minus 4 Tesla. Can we simplify this? Right, so here, right, so we have to get, this is a basic expression, right? So 2.5 represent the total angle to 2.5 radius. Then for the first arc of a segment BA, we have to get 3/4 of that. Second one, quarter of that. Then add them together. Now then try the 14th. This 14th question. So 14th question, it says, a current flows in a circular loop consisting of a single turn. Circular loop consisting of a single turn. If the same wire is bent into a circular loop of 2 turns and the same current is passed through the loop, the magnetic flux density at the center of the loop will change by a factor of. Current flows in a circular loop consisting of a single turn if the same wire is bent into a circular loop having 2 turns. The same current is passed through the loop, the magnetic flux density at the center of the loop will change by a factor of.
The 2, right? It's double.
No. Not 2. And so here, so this is the first loop and this is the second loop. So total magnetic flux is at the center of the first loop.
Increased by a factor of half.
At the center of the first loop is mu naught I over 2R. And then the total. So this is the magnet BO. represent the magnetic flux density at the center, mu naught I O 2R. Because number of turns is 1, mu naught I O 2R. Their total length is 2 phi r using the first conductor, and it should be equal to phi r dash into 2. Because there are 2 turns in the second one. Same wire is right. Same wire is rolled to have 2 turns. So same wire, the total length should be same. So by r dash into 2. So r dash we have RO2, right? Half of the initial radius. Then use this expression. Mu dash is equal mu naught I into 2, right? Because there are 2 terms. Right? N is now 2, not 1. Mu naught I into 2 over 2 r dash. And r dash is RO2. And that 2 goes to the numerator and becomes 2 into 2 is 4. Right, so this is mu naught IO2 where R is B naught. So B naught into 4 times. Right, 4 times. It would be increased by 4 times. Right, 4 times. Four times. Then try this 26th question. A long insulated wire carrying current I is bent to form a flat circle coil of n turns, and radius r. The 2 straight ends of the wire extend to a large distance as shown the magnet. So infinite long straight conductor. Flux density as center C of the coil is. Center C of the coil is 26, right? So first we identify what is the direction of the. So there are now 2 elements, right? One is the straight long conducting wire and the circular loop, right? So when you consider the magnetic flux density at the center, we have to consider of those 2 elements, right? Of those 2 elements, right? Of those 2 elements. Right. And you have to consider the direction of magnetic flux density at the center. Direction of magnetic flux density at the center due to those 2 elements. Direction of magnetic flux density at the center due to those 2 elements. So using the right hand rule, you can find. Right? You can find. So both would be outward. Right? Both the circular loop and the straight wire would generate a magnetic field in outward direction. Outward from the box, from the whiteboard outward. Right. So somehow you have to add. Right. So since the both are on the same direction, is it due to both due to both circular loop and straight wire is outward, is out. In the whiteboard. Router from whiteboard. So to find the total magnetic at the center, you have to add these two. Right? Magnetic generated by circular loop plus magnetic field fluctuation generated by the current carrying conductor, straight current carrying conductor. Right. So due to circular loop, it is mu naught n I over 2 R. Mu naught n I over 2 R. Or then due to the straight current carrying conductor, mu naught I over 2 phi R. 2 phi R. And so this is the answer. Since they are in the same direction, we can add them. So what is the correct answer? Fourth one. The answer. So here there are two elements, the circular loop and the straight wire. So we have to consider them both. To find the total magnetic flux density center. Since they are in same direction, you can add them easily. Let's try 40. It is a very long 8 parallel wires, each carries a current of 10 ampere. All carry a current of 10 ampere. The direction of the current in each wire are shown in the figure. The magnitude and the direction of the magnetic flux density produced at the center C. That is the mu naught of O is given 10 to the power minus 7. Neglect the effect of Earth magnetic field. Right? Earth magnetic field. Right, so here, right, so let's consider this conductor. Right, this conductor. So all the conductors carrying same amount of current. Consider this conductor. Here, current is flowing into the whiteboard. In using the right hand rule, you can find at the center the magnetic field is in this direction. And if you consider this one, this conductor, so here also current is flowing into the whiteboard. So if you consider that right hand rule, in that second conductor here it is opposite. But since these distances, this distance from the conductors to center and as well as the current through the conductors are same, this get cancelled out. Right? So this no resultant magnetic field due to these two conductors. That same for these two. Same for these two and same for these two. So only the resultant magnetic field at the center would be due to these two. Both would. This is the result. Now, this is 10 centimeter. 10 centimeter. So the resultant magnetic field is downward. You already know this direction. So we can find the result. Let's see. Right. So due to conductor, due to finitely long current carrying conductor, it is mu naught. Right, it is mu naught I over 2 phi r. And into 2, because there are two conductors, this one and this one. Right? So multiply by 2. Right, so in order to form this mu naught over 4 phi term, multiply both numerator and denominator by 2, then I of 4 over r. In order to form mu naught over 4 phi, then we can replace this. Mu naught 4 phi. Right, so 10 to the power minus 7 I. How much is I? 10 amperes. Into 4 divided by R. R is 10 centimeters. -10 centimeter. -2. So 10 into 10 to the power -2. Into 10 to the power -2. What do we get? That 4 10 to the power -5 Tesla, which is 40 micro Tesla. Down. Both the answer. Both. Right, so these conductors, right? So the total resultant magnetic field at the center is only due to these two conductors. Right? All the other conductors, they get cancelled out. Then try this 18th as well. 18th question. A current I flows around a closed loop as shown in the figure. The magnetic flux density produced at the center. Center. So here, Here it is part of a full circle. Right? Part of full two circles. Right, so we don't have to worry about these two. The angle theta is 0, so sin theta becomes 0. Total expression becomes Biot-Savart law becomes 0. So no magnetic field due to these two segments which are directed to the point O. Yeah. The magnetic field result would be due to this two arc, right? But here the directions are not same. Due to the first arc, it is outward magnetic field. You can use the right hand rule. And due to the second arc, it is inward into the whiteboard. So we have to get the difference to find the total magnetic field. Total magnetic at center is magnetic field due to the letter is A plus B. Mu naught. So what is the basic expression that we know? Right, mu naught NiO2R. Mu naught NiO2R. So here number of turns are 1. Two R is A. R is A. It's 2525 divided by 5/2. Right, so 25 divided by 5/2. Plus, not plus minus, opposite direction. Yes, tie to B into 25, but in order to get the quarter, that 5/2. So, not I 2, so I get cancelled out. I 2 A minus mu naught I simple B. So 2 mu naught I
So sir, for this we use the normal equation, no?
Normal equation means
The magnetic field that sends a circular shaped current carrying conductor.
yes.
That's the equation, right?
Yeah, that's the equation. Mu naught NIO 2R. And so this should be interchanged actually. These two. And so basic expression is mu naught I. That's a basic expression. That's a basic expression is mu naught I. Not I or 2R. At the center. Mu naught Ni over 2R. For a complete circular loop. But in order to get the quarter, the magnetic flux density due to a quarter of a circle, we have to divide by 2π. Right, so this is for the total loop, total circular loop. To divide by 2π and multiplied by phi over 2. Right, so it should be the other. So phi over 2 over 2π. Phi over 2, 2π. Right, so this is 8, 8. Then 8I mu naught I. Mu naught I over 8. 1 over A minus 1 over B. 1 over A minus 1 over B. Fourth one. Right? Fourth one is the answer. Yes, we have to use the basic equation, this equation, but this equation is for total circular loop, complete circular loop. But here it is not a complete circular loop. Here it is only quarter. Right? So we have to divide by 2π and multiply by 5 over 2 to get the corresponding value. Right? Right. That's why I hope some idea about how to use these expressions that we learned today for the magnetic flux density near an infinite long straight current carrying conductor and magnetic flux density at the center of a circular loop and magnetic flux density on the axis of a long solenoid current carrying conductor. So it is better you remember this, right? It's better you remember this. So the second one can be derived actually easily and combine. If you know the integration, you may try to derive this as a first expression. You can try to derive. Easily you can derive it using integration. Right. So then the Biot-Savart law. This is the most basic expression to find the magnetic flux density due to delta L element. Right. Right. So in the next session, I will focus on the force acting between two parallel conductors and move on through this magnetic field section. So that's all for this session. Thank you. Any